Hey everyone, happy Friday. It is College Friday. Traditionally, and I know this date has changed a little this year for certain schools, but traditionally, next Friday, May 1st, would be the official college signing day. It's the day you decide where you're going to college, if that's what you're pursuing. So that's exciting. That means some of you've either decided or you're making some decisions this upcoming week. I just want to throw it out there that I'm here if you need any help making those decisions. I can't make those decisions for you, but I'm certainly a sounding board if you need to talk it out, as I'm sure your parents and guardians are, and your other teachers and friends. Just know that it can be a hard decision. I know it was a hard decision for me. I didn't decide until April 30th, back when I was choosing a school. And it ended up being a great decision. So I hope that each and every one of you makes the right decision. And again, I'm here if you need help doing that. Okay. All right, let's jump into our lesson for today. Good morning. Happy Friday. Reminder, you do have an exit ticket due by midnight tonight. Otherwise, I want to jump right in to today's lesson. Now, yesterday, we started our lesson by reminding ourselves of the rules about vertical asymptotes and where those rules come from. Today, I'd like to do something very similar with horizontal and slant asymptotes. Okay. So, remember the parlance that we used. We had a function that was what we called top-heavy if the degree of its numerator was greater than the degree of its denominator. And we said, thinking about, the end behavior, the asymptote behavior of a graph like this. Okay, here's our vertical asymptote. Now, how do we find this horizontal asymptote? Well, that's simply the answer to the question, what is x approaching as we get really big or really, really small? Okay, so what happens is we plug in bigger and bigger values of x, and we keep going further and further on this graph. It's going to get closer and closer to whatever this horizontal tangent line is, or asymptote is. Sorry, it's in calculus terms. Okay, and the same thing's going to happen over here as we get smaller and smaller and smaller. And we said that when the degree of the numerator is larger than the degree of the denominator, okay, what happens as x gets really big or really small? Well, some of it's going to cancel out, but because the degree of the numerator is larger, this entire function is just going to keep growing and growing and growing and growing. So when we had what we called a top-heavy function, there was no horizontal asymptote, okay? Instead, there was a slant asymptote. And we find that slant asymptote by performing this division to see exactly what this function equals, what we're getting closer to as we keep plugging in larger values of x. Now, the next was what we called a bottom-heavy function. So what happens when we have a function like this? The degree of the denominator is larger. So what's happening as x gets really, really big or really, really small? So we thought about this. We said, well, what happens if we plug in 1 and then 10 and then 1,000 and then 1,000,000 and then 1,000,000,000 and so on? Because the degree of the denominator is larger, okay, the denominator is going to keep growing much, much, much faster than the numerator will. Which means that ultimately, okay, this -1 doesn't make a difference. This x, even though it's going to cancel some stuff out, isn't going to make much of a difference either. As we get very, very, very large, the denominator will be so much larger than the numerator, okay, that our function is going to get closer and closer and closer to what? 0. So when we had a bottom-heavy function, we said we had a horizontal asymptote at x equals 0. I'm sorry, y equals 0, my goodness. Okay, and that's because as we get really large or really, really small, same idea works here, it's just negative. Okay, but it's being squared, so it does the same thing. Then we're approaching 0 for our function value. And the last case we had was what happens when we have an equal function. In other words, what happens when the degree of the numerator and the denominator are the same. Okay, I'm going to switch this up here. I'm going to say plus x plus 2 all over x squared minus 1. Now, we could try to simplify this. Nothing's going to simplify nicely. Okay, I'll change that to 2 just for the fun of it. And as we plug in bigger and bigger values of x, either in the positive or the negative direction, okay, this value will be the same, right? We have something over itself. As we get larger and larger, once we're talking about billions and trillions and even larger, does minus 2 make much of a difference? Not really. Does plus 2 make much of a difference? Not really. And even this plus x stops mattering at a certain point. I mean, if you have a billion squared plus a billion, that extra billion doesn't make much of a difference. And so what value is this entire function approaching? Okay. Well, this is just going to be 1. So we have to turn to our leading coefficients. Okay. If this is the same and it cancels out, then the only thing that's making a difference here or whatever our leading coefficients are. Now, in this case, we have 1 over 1, so we would have a horizontal asymptote at y equals 1 over 1, which is just 1. So when we had an equal function, where the degrees of the numerator and the denominator were the same, we had a horizontal asymptote at y equals the quotient of our leading coefficients. Okay, so this is everything that we discussed earlier this year, last semester, in Unit 2b, talking about Section 2.6, rational functions. Why am I bringing this up now when we're talking about limits? Well, this idea, what happens as x gets really big or really small? That's not very exact or precise language. Okay, now, as x gets bigger and bigger and bigger, I'm plugging in 10, 100, 1,000, a million, a billion, a trillion, and I keep going, what value of x am I actually approaching? And I use value there a little loosely. We're approaching x at infinity. So a top-heavy function, or a bottom-heavy function, or an equal function, these are all answers to the question. What is the limit of a function as x approaches positive or negative infinity? What is it doing way over here or way down here? So you already know this. You know these rules. There's not going to be anything new today. It's just different notation. That's all that we're talking about here. Okay. So finally, we may need to evaluate a limit as x approaches positive or negative infinity. So what happens to the function as x gets really big or really small? This corresponds exactly to horizontal asymptotes. And how do we determine where this happens? Okay, it's the same rules as before. So this is what goes in that blank there. How do we determine where this happens? Okay, same rules as before. Top heavy, bottom heavy, equal. So nothing's going to be new. Let's take a look at some examples. Find the horizontal asymptotes for each function. Okay. So now, instead of using this imprecise language, we can use our very exact limit notation. Part A, h of x equals x minus 2 over 2x squared plus 3x minus 5. So what's happening as x gets really big or really small? In other words, our horizontal asymptotes are going to be whatever the limit as x approaches positive or negative infinity of this function is. And is this function top heavy, bottom heavy, or equal? The degree of the denominator is larger, so it's a bottom heavy function, which means that as x approaches either positive or negative infinity, negative doesn't make a difference, -1 over a billion or a trillion, that's still getting closer to 0. as x approaches these infinitely large or small values, h of x approaches 0. It's bottom heavy. So where is there a horizontal asymptote? Y equals 0. Okay. Same rules as before. All right, now we have g of x equals 3x squared minus x plus 5 all over x squared minus 4. Horizontal asymptote, that's going to be where the limit as x approaches positive or negative infinity of g of x equals. This is an equal function. The degrees of the numerator and the denominator are the same, which means as x approaches positive infinity or negative infinity, all this other stuff here matters less and less and less. And this is going to cancel out. That's just 1. So we're left with the leading coefficients. 3 over 1. This limit is 3. And so we have a horizontal asymptote at y equals 3. You all worried so much about limits all year. They're fine. This next one's fascinating. F of x equals the cosine of 1 over x. Okay, so now we have this rational function inside another function. That's okay. We're still going to evaluate using these rules. So let's think about 1 over x. Okay, this is a bottom heavy function. The degree of the denominator is larger than the degree of the numerator. So the limit as x approaches positive or negative infinity of of 1 over x, not all of f of x, just 1 over x. Okay, what happens to bottom heavy functions? We get bigger and bigger and bigger and bigger in the denominator. It approaches 0. So we're taking this 1 over x, and as we're approaching the ends of the function, this whole 1 over x is approaching 0. So what is the horizontal asymptote of f of x? We have the cosine of 1 over x, which, as we approach positive or negative infinity, 1 over x is basically 0. So we have the cosine of 0. And the cosine of 0, of course, is pi over 2 or 3 pi over 2. So we have horizontal asymptotes at pi over 2, 3 pi over 2, and of course, anywhere else, since it's a periodic function, add 2 pi. Now, this idea of actually taking this value and plugging it in, that's a little strange, okay? But we're taking this limit, and this limit we are saying does equal 0. If we could plug in infinity for x, we're saying that 1 over infinity equals 0. Okay, that's strange to wrap our minds around, but that's how these limits work. And so if this equals 0, then we plug in 0 here, and that's how we get our answer. We have one more. It's a fun one. Part D. The function k of x equals 3x cubed minus x plus 1 all over x plus 3. Now this is a top-heavy function. So the limit as x approaches positive or negative infinity of k of x, is there a horizontal asymptote? There's no horizontal asymptote because it's top-heavy. There would be a slant asymptote. But limits, a slant asymptote just keeps growing. If we look at a graph, if there's a slant asymptote, then our function's just going to keep getting larger and larger. That's not a limit, okay? It's just going to keep getting bigger. So we don't actually care about slant asymptotes with our limits, which means anytime we have a top-heavy function, we would say that the limit just doesn't exist. Okay? Yes, the limit does not exist. Now you understand what that means. Because it's not actually going to approach any value. Okay? So the way we write that, again, mathematicians, we like to be as succinct, some would say lazy as possible. This limit does not exist. We abbreviate that as DNE. DNE does not exist. So the limit doesn't exist, so there's no horizontal asymptotes here. And there we go. God, I've been waiting to make this connection to limits since Unit 2. I'm so excited that we finally get to talk about this. So we'll practice a lot next week. Okay, so this 9.1 exit ticket is going to be your last new learning target grade in the gradebook for the year. After that, you'll only have your culminating activity. So this weekend, make sure to review, rewatch any of these that have confused you, and get started on that culminating activity that's due 2 weeks from today. Okay. Make sure to get that exit ticket done by midnight tonight, work through the 9.1 independent practice, and come to me with any questions you might have about limits. Otherwise, I'll see you on Monday. All right, well, that was our lesson taught by yours truly. It sure is nice not to hear that buffoon Boothman. Reach out to me with any questions. Otherwise, have a great weekend, and I'll see you on Monday.